I almost had a heart attack.
Yeah, the check mark's like, oh. So I have a couple of review slides. Specifically, we're going to talk more about radiation coming from the sun, and I kind of told you we'll have another kind of energy diagram where 100 units of energy come from the sun. What happens to that 100 units of energy from the sun when it interacts with the Earth's atmosphere and the geosphere? But in the meantime, I just kind of wanted to remind you about these laws of radiation, okay? Specifically, here in a minute, we're going to talk about this number 4, okay? Basically, if something is good at absorbing radiation, remember radiation is all those cousins. Radiation starts with X-rays and ends with radio waves, okay? All those different forms of radiation. But if something absorbs radiation well, then it also re-emits the radiation well. And we're going to see that here in a minute. The other thing, and this is a review slide, right off the bat, we're going to talk about radiation. We're going to talk about when the radiation comes from the sun, there are a few things that can happen, okay, with regard to our atmosphere. And these down here are the few things that can happen. And it depends, like I said Monday, that it depends on which energy it is and what particle in the atmosphere it's interacting with. So one of the things, starting with absorptivity, one of the things is that basically the energy, this should be a new slide. Okay, you guys all okay with this new slide? So basically the energy coming via radiation from the sun can be absorbed by the particle, okay? And in general, if something absorbs energy from the sun, it's going to heat up. The amount of energy or the degree to which that particular particle takes in that particular energy is called absorptivity. Makes sense? Okay. So like I said, in general, it heats up when absorption occurs. An example of absorptivity we already looked at is that good ozone in the stratosphere, right? The good ozone actually is great at absorbing one particular energy, ultraviolet radiation from the sun. So that's one of the things we need, that the stratosphere, we need that good ozone layer in place. And it's mostly in place except for the springtime, right, at the poles. So when somebody talks about the ozone hole, don't get all freaked out. I often think, because remember we talked about kind of the localized hole near the poles, I thought maybe that's just the place to avoid in the springtime. I don't know. I know, it's a thought. But another, for instance, a kind of absorptivity that can occur is the particle isn't ozone, but the particle is water vapor. So we're going to talk a lot about water vapor. Like in this room, there's a certain amount of humidity. We have water vapor in this room. And on a hot summer day, if the humidity is high, quite honestly, those water vapor particles in the air, because the humidity is high, actually can interact with energy from the sun. Okay, now I know humid days we feel very hot, and that's hot and muggy, okay? But actually they can take some of the intensity of the sun's rays away. So I know, something to think about. So bring on the humidity, right? No, I don't know. Right. So that's absorptivity. So we said the particle can transmit the energy from the sun, like blow it off, I don't care, it's there. The particle can absorb energy from the sun, or that particle can have some sort of interaction we call reflection, okay, reflection or scattering. So that's what I'm going to talk about here. So the yellow is the stuff from the sun, okay, and these white little things are particles in the atmosphere. These are particles in the atmosphere. They could be nitrogen, okay, they could be oxygen, they could be snowflakes, they could be liquid water particles, okay. So it just kind of depends, and we'll have different outcomes, okay? But when we talk about reflection, reflection is like a mirror. So like if you look in the mirror, you know the image is going to come back to you. That's reflection. It's a known path. That light is a known path. Kind of more random we call scattering, or even backscattering. So see, to me, like the slide says, in this little slide, this isn't reflection. This is actually light just randomly being scattered. Okay. Did you get that?
No.
Oh, sorry.
Sorry.
Oh, you're fine.
Okay.
And I tried to look up, because to me scattering and backscattering, I was like, what's the difference? Well, it's a subtle difference, and I won't test you over it, quite frankly. Okay.
So we don't need to know the difference between scattering.
Right, you don't need to know the difference between scattering and backscattering. You do generally need to know what scattering is, and maybe the difference between reflection and scattering.
Are you going to give us a study guide?
I'm going to give you a study guide, yes. Okay, so we have absorption, no, albedo. So reflectivity, this is all about reflectivity. Okay, we have two words that deal with, like, basically light hits something and it's kicked back. Albedo, we talk about the albedo of an object, that's basically kind of how much light or how much energy that object is going to kick back. Okay. Reflectivity is the same as albedo, but it's in percent. So I'll kind of show you what I mean by that. So one of the things I talked earlier, you guys already know, is that if it's a sunny day outside, okay, and if you want to stay warm, you wear something dark colored. If it's a sunny day, you wear something dark colored, because you know something dark colored is going to absorb the light, okay? So if something absorbs the light, and we have some examples here, the wet plowed field, okay, something absorbs the light, it has what we call a low albedo. It has a low percent reflectivity. Okay, so something dark down here, that's relatively low albedo. Now, I said albedo and percent reflectivity basically differ by a factor of 100. So if this is the percent reflectivity, the albedo would be 0.15 to 0.25. See how that works? It's just like the decimal version of percent reflectivity. Albedo and percent reflectivity, they're saying the same thing. So grass, okay, it's percent reflectivity. So if it only reflects 5 to 25, then that means it absorbs what? 95 to 75. Does that make sense? Okay. So a low reflectivity means a high absorptivity. Down here, water can vary a lot, okay, depending upon what kind of roof you have, right? Clouds, depending whether they're thick or they're thin, there's their reflectivity. Right? So not only color, but actually texture, and this kind of makes sense. If you go back to the wet plowed field, I could almost, see the grooves. It kind of gets down to the nitty gritty. The grooves in the kind of the clunks of in the soil. They can actually be good at sucking in and less at reflecting back. Does that make sense? So it's a texture thing and a color thing. Yep. All right. So remember when I had this chart up here for the different types of energies, and I said, because at the top was gamma rays, right? The top was gamma rays, and at the bottom was radio waves. Okay, and somewhere in the middle was visible light. It's like this is a sliver of energies of radiation, electromagnetic radiation. But of course, visible light is why we see things. Thank goodness for visible light. I just think it's just amazing if you think of the biology of your eye, which I don't really know anything about, but it's just amazing. Have you ever wondered, like, when I see something green, is it the same green to you, or is it like blue to you? And we just call it the same. Yeah, it's like, wow. Wouldn't you wish you could see through somebody else's eyes sometimes? Anyway. So when we see something, for instance, I put blue up here. When you see something blue, that actually is the color that's reflected, okay? So it kind of looks like this. If this is a blue shirt, okay, basically it could be light from the sun, okay? The thing about the sunlight is it is sending all colors of visible light. So coming from the sun, I usually go Roy, G, not Roy B, but Roy G. Viv, okay? That's all the colors of white light. Okay, so basically what's being reflected is blue, okay? So what's being absorbed is everything else, yep. So that is, let's see, Roy G. Iv. Roy G. Iv is absorbed. So, see how that works? All right. So along those lines, if we talk about the extremes, the whole black and white, okay, so the extreme, so black is an extreme. So black basically, if I draw a shirt again, if something's black, basically all colors are absorbed and none are reflected. Mm-hmm. They're all absorbed and none is reflected. Has a very low albedo, low percent reflectivity. If we look at something that's white, basically white light hits it, Roy G. Biv hits it, and Roy G. Biv is scattered back. And this is where our eyeballs, I just think, are so cool. Our eyeballs actually mix those wavelengths from their components back into a composite white color. Isn't that cool? I know. So if something's white, everything's reflected. It has a high albedo, a high percent, 100% reflectivity, kind of like that.
How does like tie-dye work then when it's all those different colors?
It just, to me, you're like imparting, tie-dye, you're imparting different pigments to your shirt, and so they work independently of each other. So the reds come from something and the blues come from something, but they're all, yeah. That's a good point. If you were wearing a tie-dye shirt that had Roy G. Biv, if you go fast, you're gonna look white. I don't know if that makes sense. But have you ever seen one? There's actually these little color wheels. If you take a color wheel with all of the colors, which would be kind of a tie-dye shirt, and make the color wheel go really fast, it looks white.
I'm a magician.
What?
I said I'm a magician.
You're a magician? You can do that?
I've done that
So-
with tie-dyeing before. I was confused when my shirt was still white.
Your shirt was still white?
Yeah.
That's
But then
magic.
when I put it back in the thing, it was like different colors of the hair.
Yeah. But kind of like this, okay, so black light, the whole black light, have you guys ever like played around? So when you do black light, you're basically sending, not like Roy G. Biv, you're sending a selective color. Yeah, and like if your shirt is not that color, there's different interaction, okay, from that, because this is white light, it's Roy G. Biv, but if you send just violet and you're wearing something red, how does that work, right? Anyway.
I was being sarcastic.
Okay.
I'm not a magician, but anybody could do that.
All right. So if you go really fast with a tie-dye shirt, it looks white. I like that. All right. So for this idea, I'm going to bring a stool out here, okay? And we'll just, well, this is the sun up here, okay? Our projector is the sun. So the sun is like a 90-degree angle sort of thing, okay? So this is direct and diffuse light. So just in general, would you say that there's where's the shadow? Underneath there. So there'd be, if we got this whole angle thing going, we had a nice little circle shadow there, right? So basically, why is that shadow there? Because this thing is blocking light, right? It's blocking direct light. That's going to be my point, okay? If I put like a pen or something underneath in the shadowed area, a sunny day, I'll probably still see the pen, won't I? But honestly, I'm not seeing the sun because, I'm not seeing that pen because of direct light, because you guys told me that stool is blocking out direct light. Yeah, I'm seeing it because of scattered light, exactly. And I was thinking about this today, getting ready for this lecture, I'm like, there is a lot of things, a lot of energy things happening that we just totally blow off, A lot of energy transfers. We're like, okay. Yeah, but the fact that you can see that and it's in the shadowed area, you're not seeing because of direct light, you're seeing it because what we call diffuse light. It's kind of just this random ping-ponging of light. So one of the things, and I haven't chased it down, but if you're like me, you wonder about a lot of things. If you've ever watched the Mythbusters, they're good at chasing down different things. But the reason we have kind of diffuse light or scattered light has to do with the fact that the Earth has an atmosphere. Now remember, actually, here, one of our few last slides, we're going to look at other planets and the atmospheres around other planets or around the moon. But if you go to the moon, it's not an atmosphere, it's called an exosphere. The moon basically it's not big enough, it doesn't have the gravity capabilities. Basically, the moon is oozing a certain amount of gases that just escape. Okay? But on the moon, if you don't have an atmosphere, you don't have this pinging around, you don't have this kind of backscattering or scattering of light. So if you would do the same thing on the moon, I don't think you'd see the pen. I really don't think you would. In the daytime on the moon, but oh my gosh, don't get me started, because actually this gets to this idea of the daytime on the moon. If you were on the moon in the daytime, you would see the sun. It's a star, right? You would see the star, a big old star, our sun. Okay, but the skies would be black. The skies would be black on the moon in the daytime. And so that gets to this idea. Why are our skies blue? My husband likes to come up with funny things, and he said, well, the sky is blue, so something about when you're mowing, you know when to stop mowing. Right, I know. But the sky is blue because of the scattering. And the scattering is there because of we have an atmosphere. Specifically, remember, most of our atmosphere is nitrogen. It's about 80-20, nitrogen, oxygen. The nitrogen molecules are pretty good at scattering a select wavelength of light. The shorter, the better. So if you think of Roy G. Biv, your short ones are the Biv. Blue, indigo, violet. Yep. So that is actually that kind of ping-ponging, selective for those wavelengths that nitrogen gas does, is kind of what gives us our blue hue to our skies. Is that not cool or what? So they call that Rayleigh scattering. I'm not sure your textbook uses that term, but I do. And this scattering has an enhanced effect when, when the sun is low on the horizon. We talked about angle in here, okay? So, did we talk about angle in here? I think we did. Okay. So if the sun's straight up, okay, which wouldn't necessarily be, remember at noontime, near the winter solstice, the sun actually, the highest it gets is not very high, and then it goes ahead and sets, okay? And we talked about this angle thing. We said that when the angle is small, we get beam spreading. Remember that, when the angle is small? When the angle is small, also we get beam depletion. I don't know if you remember that. And actually that kind of leads to this. Beam depletion is because when it's a small angle, basically that shaft of light has to go through more of the atmosphere. And that's why our skies are kind of red or orange at morning, at night. And that's I like this figure in your textbook. So when I was shopping for textbooks for this class, this one caught my attention. Because what it's trying to show you is we have the scattering out. So this is when the shaft first comes from the sun, entering the Earth's atmosphere. So we have scattering, scattering, scattering. So basically at some point it kind of scatters out all of the short wavelengths, the blue, indigo, violet. And so what it leaves coming is just kind of those longer wavelengths, the red, orange, and yellow. And that's kind of when the sun is low on the horizon. If you were to hold up something white, like a piece of paper, to the morning sun, that piece of paper is orange. It's very pretty. So to me, that's an indication of, well, what's coming from the sun? Orange. Why? Because of Rayleigh scattering. Okay, it's beam depletion in a sense, because the small angle has more of the atmosphere to go through. All right, crepuscular rays. It sounds terrible, but it's actually a very pretty phenomenon. This is one of the things I looked up to make sure I got it right. But because your textbook, I think, kind of falls short just a little bit, But in order to get crepuscular rays, you have to have something irregularly shaped. It could be a mountain or it could be a cloud. Have you ever seen these rays, by the way? They're so cool.
I have a picture.
Pictures would be nice, yeah.
They're incredible sometimes.
They are. They just make you pause and go, oh my gosh. Now, if you can either see them in the morning or late in the day, okay? But as the sun gets higher, then the effect kind of goes away. So, in chapter 16, we'll kind of talk about this like diverging. It almost looks, doesn't it look like these rays are kind of diverging from a certain point? But actually, it's an optical phenomenon. They're not at an angle like they're what we call parallel. It's very similar to a railroad track. Like if you stand at a railroad track and look down the railroad tracks, don't they look like they're going together? They're converging. Okay, that's kind of a similar phenomenon. So anyway, crepuscular rays. I like them. And pictures would be nice. All right. So when I opened the slide about the fourth law of radiation, I said if something is good at absorbing energy, it's also good at re-emitting the energy. So if you talk about the spheres, the atmosphere and the geosphere, the atmosphere, air, oh my gosh, it just doesn't, air in and of itself doesn't absorb energy very good. If we're hot, you know why we're hot? Probably because the geosphere is hot. The air can, put another way, haven't you ever been out on kind of an intermittently cloudy day? You know, like you have these big clouds, clear, big cloud, clear, big cloud. And like if a cloud, bless you, if a cloud moves in front of the sun, right away you feel cooler. I mean, that air will kind of respond, okay? So the air doesn't absorb it, okay, and it doesn't emit it very good. Now, the geosphere, so when I say the Earth's surface, okay, be thinking geosphere, right? It's like 80% instead of 20% compared to the air. So it really can absorb it, and it actually can re-emit it. I almost think of as the Earth, you know, in a course of a day, as it has the sun, and then it goes nighttime, and it has the sun, it has nighttime, spins on its axis of rotation. It's almost like the geosphere soaks up the energy and kind of re-emits it during the night, and it soaks it up again. Now it's oozing energy during the daytime too, but it really oozes it at night, I think. All right. So this is why this whole idea of the geosphere heating up, this is why in this layer of the atmosphere we call the troposphere, where all our weather is, that's why as you go up in the troposphere it gets cooler, because you're going away from the kind of the radiator. All right. So on the next slide, this to me kind of talks about almost kind of transparency. So we've talked about, here today we talked about, you know, stuff in the atmosphere can either transmit the energy, okay, it can absorb the energy, or it can scatter the energy. Those three things, those three options, okay? And this kind of collectively looks at the stuff in our atmosphere and what it does to different wavelengths. We are lucky that harmful shortwave radiation like gamma rays and X-rays are the way our Earth's atmosphere is structured. Those things are blocked out. So here is, I don't know if you recognize kind of the called radiation curves up here. The red line is kind of the fingerprint of energy that the sun is sending out. Okay, and here we have short wave, high energy over here. Here we have longer wave radiation over here. And this is kind of the squatty. Remember, this is following kind of the laws of radiation. You would say our Earth is a lot cooler than the sun. So the second curve actually is our Earth's curve. Okay, so it's squatty and over here to the longer wavelength. So that's kind of what you're looking at. So here we go. Here are some gases in our atmosphere. Nitrogen, I don't know if you can see that, that's N2. Okay, nitrogen. 80% of our atmosphere is nitrogen. So the way you look at this is, let's see, absorptivity. All right, so the y-axis is absorptivity. So basically where you see nothing, okay, where you see nothing, that means that nitrogen allows all of these wavelengths to come in. and it absorbs these wavelengths. Okay, so that's how nitrogen works. Now I'm going to show you the next gas. And actually kind of combined here, we have our regular oxygen, which is O2, and then we have our special oxygen, which is O3. Of course, O3 is ozone, and the good ozone is in the stratosphere. But this is where, remember we said that ozone is good at absorbing short wavelengths like ultraviolet radiation. Okay, so we have both O2 and O3 kind of showing absorptivity over there. Carbon dioxide and water, those are two variable gases, aren't they? So remember, variable gases means they vary by location and by, they vary by location and by day. So we kind of had these weird sort of columns of absorptivity. And the last one, I'm going to kind of show them all together. But we talked about the greenhouse effect in here, didn't we? I kind of lose track. Here, this red bar right here, kind of this red bar, that's heat, that's infrared, that's thermal energy. So kind of the greenhouse effect is being shown right here, this kind of absorptivity of that particular energy. Okay, the greenhouse effect. Remember we said that as the Earth oozes its radiation, they actually trap it, and carbon dioxide and water vapor both do that. So kind of as a whole, it's shown here. So if you were to take kind of all of those like blue areas of the nitrogen, the oxygen, the ozone, the carbon dioxide, and the water, and kind of combine them, you would get kind of that blue area down there. Okay, so this is good. This is happy. Okay, we want basically our atmosphere to block those short wavelengths. Okay, this is kind of a little bit random. This right here actually is important because the whole thermal part, the red part means heat. Okay, we kind of need the Earth to be able to cool off. Okay, so we want to leave that window open, quite frankly. It's an important window. So that's how that works. Clouds are kind of hit and miss a little bit. Okay, they're hit and miss because of the thinness and the thickness of a cloud. Okay, the thick clouds give you more effect, the thin clouds give you less effect. But the other thing is the cloud there at night or is the cloud there during the daytime? They have the opposite effect. So during the day, the presence of clouds is a cooling. I mean, it kind of makes sense. During the day, yeah. It's going to either absorb or reflect that incoming energy from the sun, you know. It has the opposite effect at night, though. Clouds at night will keep you warmer. Yep. They actually, clouds at night act as kind of a, and again, it depends on thickness and kind of probably the elevation of the cloud, but kind of think of them as a cozy little blanket, okay? Because at nighttime, basically, you're turned away from the sun. Okay, at nighttime, the only thing you got going is basically the Earth re-radiating the heat that it picked up during the daytime. So if you have a cloud at night, you might have a,
Bounce off.
yeah, you might have a chance for that thermal energy not to escape, but kind of bounce off. Yeah, so some of our most bitterly cold nights are when it's clear. And you want to go out and get your telescope out, and it's just freezing
No
cold.
wind.
What's that?
Clear and no wind.
Clear and no wind, yeah. So they kind of have a mixed effect. Oh, we didn't talk about the greenhouse effect yet. Oh my gosh. Okay, so here's the greenhouse effect. Remember we saw water vapor and carbon dioxide kind of have that little bit of blocking there with regard to infrared radiation. Of course, the greenhouse effect, you need a greenhouse, right? But this really actually works in your car. On a sunny day, forget the greenhouse, okay? On a sunny day, no, don't forget the greenhouse. If the sun's light can come through your window for your car, okay, and if, like me, you have black upholstery, okay, which is good, I think, that black upholstery will suck up that light, basically light energy from the sun, okay? And if it sucks it up, okay, it's basically going to, that energy is going to be converted from light to heat. You can go ahead and go back and forth between these radiations. It will be converted from light to heat. So basically, the molecules in your car upholstery get going faster and faster and faster. It's hot. So, all right, so it's ready to go ahead and send that infrared radiation back out. The thing about glass, visible glass, it's like a greenhouse. Glass will let visible light in, okay? But with regard to thermal energy, not so much. Thermal energy pauses. I'm not saying like you wouldn't go like measure the temperature right on the other side of a greenhouse and say, oh, well, that's warm. But it doesn't transmit thermal energy like it transmits visible light. Okay, so that's kind of what's going on. So that's the greenhouse effect. Visible light comes in, heats up something, okay, then the thermal energy doesn't get past the glass. So here we have SW stands for shortwave radiation. Visible light is an example of shortwave radiation. And LW stands for long-wave radiation. And infrared is an example of long-wave radiation. So that's kind of how that works.
What do you write in the long box?
What's that?
There's like an empty long box.
Must not be anything there. Nothing in the long box. Okay. So some pictures to kind of show you the greenhouse effect. A clear day, right? All that light, all that energy coming in. Remember the geosphere absorbs about 80% and is going to re-emit 80%. Right away during the daytime, it'll start re-emitting. Okay, but it also kind of retains that for the nighttime effect. Okay. It converts visible light. Some of that energy is absorbed and re-emitted as those little red things are infrared radiation going up. The little things that look like bugs or bees, actually, if you look closely, you'll see that they're water molecules. Okay, water molecules and carbon dioxide molecules. So they, like we saw a minute ago, actually are good at absorbing infrared radiation, long-wave radiation. So then what they do is kind of a scattering thing. They absorb so they can become warmer, but remember, the atmosphere is not a good absorber or re-emitter, but they kind of scatter the energy in all directions, scatter that thermal energy in all directions. So in a sense, they kind of act like a blanket. The greenhouse effect. Oh, you guys don't have this one, do you?
I was wondering
Drawing
why.
pictures.
Oh, okay. You have to draw the pictures.
Yeah.
If you get Twitter feed, if you get it, man, I'm going to go ahead and take a snapshot of this, and I'm going to put it up under the Twitter feed for this is the missing slide. So.
Nice job.
All right.
Sorry.
Okay. All right. So the moon, starting with the moon here, does not have an atmosphere. The moon was beautiful this morning. Did you see that kind of the waning gibbous, and there were some clouds in the west? It was very pretty. So anyway, the moon doesn't have an atmosphere. So basically what's being shown here is it can absorb thermal energy, or excuse me, it can absorb radiation from the sun, convert it to thermal energy. That's the red, and basically there's nothing there to stop it. So the daytime side of the moon could be warm, but the nighttime side of the moon would be very cold. This is the Earth, where basically we have greenhouse gases, those little white particles, that actually can keep some of our thermal energy in. And this is Venus, which if you've studied the planets, sometimes when we talk about Venus, we say it actually has a greenhouse effect, but it's a runaway greenhouse effect. So like our atmosphere is mostly nitrogen, that planet, the atmosphere is mostly carbon dioxide. So nitrogen doesn't interact with thermal energy, but carbon dioxide does. Okay, so it's very hot on Venus is my point.
We couldn't live there.
What's
I
that?
don't think we could live there.
No, I don't think we'll live on Venus. Nope. So this is like another energy budget diagram, where if we kind of track it a little bit, if we pick on 100 units coming in, now again, you're like, you know, what's the cloud cover going to be like? How many clouds and what sort of clouds? Well, they just kind of randomly came up with some. About 50 of those units are going to be absorbed by the geosphere. About 20% are going to be intercepted by clouds, and about 30% aren't going to make it past these particular clouds. of those 50, now this is kind of exciting.
And that 50 plus just means the percent?
Right, percent, yep.
Yeah.
Because they're based on a kind of a randomly 100 units, so it would be the same as percent, exactly. So of those 50 units or 50% that come down, it's kind of cool, no pun intended, but basically all of those units are released by the Earth if things are working correctly. And how are they released by the Earth? Well, one is from convection, we talked about convection. One is through evaporation, we talked about latent heat of evaporation. When basically water goes from a liquid to a gas, it takes some energy, and that's a cooling effect for the geosphere. One is just kind of oozing it via radiation back to the atmosphere. Okay. Now, I'm going to have to, the last slide, actually the last topic kind of qualifies this. I'll say a typical heat budget at about 38 degrees north or south latitude. Our energy budget is about what comes in and goes out. And what I mean to say is, let's see, 38 North America. 30, 45, 38-ish.
That's Missouri.
Okay, Missouri. Okay, I'll buy that. So about Missouri, their energy budget, what comes in goes out. Yeah. So let's take a look at how that works. So by latitude, throughout the course of the year, so this is like net annual radiation, so like the whole year, you know, the Earth orbits the sun one time throughout the year. Who gets extra radiation and who gets less radiation with regard to coming in and going out? So you guys probably would say the equator. Actually, if we were to do an energy budget diagram like I just did, they would have, they might have 50 units coming in, but they'd only have like 25 units going out. So they would have what's called a net surplus. Okay, they have extra energy. Okay, the poles, again, it has to do with kind of the angle of the sun throughout the course of the year, but on an annual basis, if you get on either side of 38 degrees north or 38 degrees south latitude, okay, they're shown right here. So this is by latitude. So the way you read this, you guys are getting good at reading figures, by the way. So this is the equator. Okay, and this is north, and this is south. Okay, and then the tipping point is 38 degrees. Okay, we have a surplus from the equator towards 38 degrees, and we have a deficit from 38 degrees towards the poles. Okay, just in general. Cool. So, was that the last slide? So we're gonna do something different. We're gonna actually take a look. Indulge me, please. We're gonna take a look at your homework questions. So we're all kind of on the same page. So, if you have your homework sheet, right, you can see that you've got give it some thought 2, 4, and 5. So here's 2, here's 4, and 5 is coming up. So 2, 4, and 5, give it some thought. The first one should look something like the whole bucket in yeah. The 4 says, which of these 3 mechanisms of heat transfer is most significant in the following? So for instance, how does heat go, oh, a seat heater, I got a seat heater in my new car. So how does, like, if you turn on your seat heater, how does heat go into your butt? Okay. Would that be, remember our options are conduction, convection, or radiation. Those are your 3 options for those, okay? So that's 4. Number 5 looks something like this. 5 is a fun one. 5 says, it gives you A through D diagrams of the Earth orbiting the Sun and asks you, I can't even read that, which of these is most accurate, which of these, identify what's wrong with each of the other ones. Now I'm going to look at what I gave you. So for instance, for problem number 5, notice there is no asterisk. So for problem number 5, I'm going to be looking for complete sentences. Okay. The last one under give it some thought, okay, looks like this. Okay, again, no asterisk, so you got to do complete sentences here. Rank these in order according to the wavelength of radiant energy each emits from the shortest wavelength to the hottest. So my hint for you is shortest wavelength. Would that be hot or cold? Short wavelength, is that high energy or low energy? It is high energy, so it would be hot, exactly. Shortest wavelength would be your hottest. Longest wavelength then would be your coolest. Yep. So I wish, let's see, while I have you here, that looks to me like rank the following. You should be able, you shouldn't have to use complete sentences for that. So if you're if you could hear my voice, put an asterisk next to number 8, because you should not have to do complete sentences for that.
Number 8.
For number 8, yeah. I think you can just rank them. Then the last one is a problem. Let's see what it looks like. Oh, yeah. Okay, so this one actually we talked about the noontime sun gets this high in the winter solstice, and the noontime sun gets this high at the summer solstice. That's exactly what this diagram was talking about. How high is the sun? So, let's see. Let's read the question. I picked it out. So according to this graph, we should be able to determine the latitude when the sun is at any date. So let's see. So for instance, which latitude of the vertical noontime sun? So, and oh, I see. So let's pick, what's today? Today is January, what's the date? 27th? Okay. So January 27th, let's find January. I see 25 and 30. So somewhere in there would be the 27th. Okay, January 27th. So the way you do that then is you read who's going to get the vertical noontime sun. You have to go over here. And to me, it's 18 degrees south latitude. See how that works?
Can you have points on those, or do you just want direct numbers? Between and so I put a point. But I don't know.
Points? I'm sorry. So do I have points or just numbers?
Like 18.2.
Oh, I see what you're saying. Can you kind of get to the...
Or do you just prefer us to say it's 18, or whichever one is...
I'll take either one. I like what you're saying because you're saying you can almost kind of estimate between the little marks. Yep. And if you can, I would. But if you don't want to, I'll probably...
Okay.
For something like this, when I'm grading them, I'm giving like plus or minus... It depends, but plus or minus 5 units or something.
Does
So.
it have to be in full sentences?
What's that?
Does it have to be full sentences?
This one does not have, because it has an asterisk.
It does.
Wait. Yeah. No, it doesn't. Oh, put an asterisk next to that one, too. I was just... Okay. Thank you for pointing that out. All right? So I hope this was helpful. We'll probably do this with other homework, too. Okay, that's all I have today. Do you guys want your chapter 3? Let's do that. So chapter 2 is due Friday. And bring these with you on Friday. I'm trusting you.
Hey, I want to apologize for laughing at me. I was not laughing at you. I'll show you what I was laughing at.
Okay, you
Hold
did.
that thought.
Oh, good grief. And I asked you,
Thank you.
It's a greenhouse effect, but no. It's nice.
I saw you drawing something and you snickered and I looked over and I'm like, what are you doing?
When I start laughing, I don't have to stop.
I noticed this.
What were you?
Look what he drew. That's why I couldn't stop
It's a
laughing
greenhouse effect,
either.
no.
Oh my gosh. All right.
When I start laughing, I have a hard time stopping. So.
I need to see this real quick.
Okay.
I got another class.
Oh, sorry, you can have it.
No, it's like, I want to remember what I wrote.
Can you take it out? Okay.
What's that?
Is it for this class?